Hello everyone, welcome back to our Math for Machine Learning series. In the last few videos, we learnt about linear independence, basis vectors and matrix rank. Basically how vectors and matrices define and span space. Today, we're taking it one step further to understand how matrices actually transform space, specifically through something called the determinant. By the end of this video, you'll know how to visualize what a determinant really does and why a determinant of 0 makes a matrix non-invertible, or in simple words, impossible to reverse. We'll start with this big idea. Think of a matrix as a machine that transforms space. It can stretch, shrink, flip, or rotate it. The determinant tells us how much this matrix scales space. It's like a scaling factor in 2D, specifically for area or volume in 3D. Imagine you have a simple 2D square with an area of 1. If you apply a matrix whose determinant equals 2, the square becomes twice as large. Now, area will be equals to 2. Similarly, if the determinant equals 0.5, the square shrinks to half its original area. And if the determinant is negative, the transformation flips the space like a reflection and also scales it by the absolute value of the determinant. So basically, determinant tells you how much bigger or smaller does the transformation makes everything. Now think in 3D. Imagine a cube. The value of determinant tells you how its volume changes. If the value is 1, the cube keeps the same volume. If the value is 3, the cube's volume triples. Or if the value is 0, the cube collapses into a plane or a line. That last one is important. If the value is 0, the transformation squashes space, meaning you lose a dimension. Here is a very nice geometric way to picture it. In 2D, if you take two vectors forming a parallelogram, the absolute value of the determinant of the 2 by 2 matrix formed by those vectors equals to the area of that parallelogram. Similarly, in 3D, if you take three vectors forming a parallelepiped, then the same value gives you its volume. So, determinant is basically the measure of space scaling under your linear transformation. And why does it matter in case of ML? The value of determinant helps us find out whether a matrix collapses space. If the determinant equals 0, that means the transformation flattens space and such a matrix is singular, meaning it can't be inverted. This matters a lot. For example, in case of linear regression, if the value of determinant of x transpose x equals 0, then we understand that the columns of x are linearly dependent, which means your model can't find a unique solution for its weights. So in short, the value of determinant tells us how much a matrix stretches, shrinks, or flips space and whether it's even possible to reverse that transformation or not. Now we consider this case. We'll dive deeper into this idea of when the determinant is equal to 0 with few clear examples. We'll see why if the value is equal to 0, that means you can't go back, or why the transformation becomes non-invertible. We'll take a simple 2 by 2 matrix that works fine here. So you can see that we have matrix A here, and then this particular matrix A is just an identity matrix. It keeps every point exactly where it is. If you take the unit square and transform it with this matrix, you get the same area, which means area equals to 1. If you compute its determinant value, then you also get it as 1, which means the area actually did not collapse and we can easily go back, which means the inverse is itself here. We'll take another example B. If we compute the same value of B here, we get the value as 0. Now what does that mean geometrically? So if you take two column vectors the first column vector 1 and 2 and the second column vector 2 and 4, you'll notice that the second column vector is just twice the first. That means both lie on the same plane. They no longer form a 2D plane. So when you apply this transformation, your entire square flattens into a line. Area becomes 0, you've lost a dimension. And because multiple points from the original space gets mapped onto the same line, you cannot reverse the transformation. That's why we say if we get the value of determinant as 0, that means it's non-invertible. Consider the data set that I provided here. You can read this as feature 2 equals 2 times of feature 1. That means both features lie on the same line in space. So when you form the matrix X with these columns, the columns are linearly dependent. The data effectively lives on a line, not a plane, because if we compute the value of determinant of X transpose X here, it equals to 0. And then when you try to compute the inverse for regression, it fails because the model doesn't have enough independent information to find a unique solution. So whenever the value of determinant equals 0, it means one or more of these things has happened. 1. The matrix collapses space, area or volume goes to 0. Second, the columns or rows are linearly dependent, which means no new direction is added. And third, you've lost a dimension. So the transformation can't be undone. That's why we call such matrices singular or non-invertible. So in one sentence, we can say that when the determinant equals 0, your transformation has squashed space so flat that there's no way to go back. The information is gone. And that is the power and the danger of the determinant. So this is all for this video. I'll see you in the next one.